How the ingredients of a tornado. The power of a tornado begins far above the ground, long before any rotation sets in, inside a storm system known as a supercell. The supercell is not a simple thundercloud, but a highly organized engine in its own right, containing a mesocyclone, which is a rotating updraft that becomes the seed of the tornado. Before rotation ever begins, the atmosphere must first prepare an environment of extraordinary instability. This process begins when warm, moist air from near the ground rises into cooler, drier air aloft. The greater the temperature difference, the more energy the rising air contains. In meteorological terms, this instability is known as CAPE, or convective available potential energy. High CAPE values mean that parcels of warm air can accelerate upward at astonishing speeds, sometimes exceeding 100 miles per hour. The air is effectively launched into the sky like a rocket, feeding the towering anvil-shaped cloud that dominates a supercell. However, instability alone does not create rotation. Tornadoes need wind shear, changes in wind direction and speed with height, which creates horizontal tubes of rotating air that are invisible but very real. When a supercell develops a powerful updraft, it tilts these horizontal rotations into the vertical, producing the mesocyclone at the heart of the storm. The mesocyclone is vast, often several miles wide, and its rotation is deep enough to influence the entire structure of the storm. Every tornado begins as a small part of this much larger rotation, and the physics of this transition marks one of the most dramatic transformations in the natural world. Before the funnel ever touches the ground, the atmospheric blueprint is already in place. The ingredients, moisture, heat, instability, and shear work together to create the atmospheric stage on which the tornado will be born. The forces at work are so large, they span counties, and so delicate that even minor shifts in wind speed can determine whether a storm produces a harmless cloud or a destructive vortex. This is nature's precision engineering, crafting the conditions that allow one of its most powerful engines to ignite. How vorticity and updrafts create the tornado core. Once the atmosphere has created the ingredients, the tornado's birth depends on vorticity, the measure of how much a fluid, in this case air, spins. A tornado is essentially a vertically stretched vortex, but the creation of that vertical vortex is the result of processes that stretch, intensify, and reorganize air currents within the storm. As the storm's updraft strengthens, it becomes a vacuum pulling air upward with enormous force. This rising motion stretches the rotating air column, and just as a figure skater spins faster by pulling in their arms, stretching a vortex vertically increases its rotational speed. This is known as angular momentum conservation, a principle that governs tornado dynamics on every scale. What starts as slow, wide area rotation in the mesocyclone becomes faster, tighter, and more concentrated. Low pressure forms at the center of this column, which further accelerates the inward collapse of surrounding air. The more tightly packed the air becomes, the faster it spins, and the faster it spins, the lower the pressure becomes. This feedback loop is what leads to the birth of a tornado. The mesocyclone begins to narrow into a funnel cloud, visible as condensation begins forming from rapidly cooling air. The cloud descends toward the ground not because it is falling, but because the rotation intensifies downward. At the same time, air at the surface is drawn upward, meeting the descending rotation halfway. The tornado engine. To understand the physics behind tornado power, one must consider the tornado not as a column of air, but as a heat engine. Tornadoes function because of extreme pressure differences and rapid temperature changes, which create powerful inflow currents and sustain rotation. The core of a tornado can have pressures as low as 100 millibars below the surrounding air, making it one of the most dramatic pressure gradients found in nature. The speed of this rotation is governed by the conservation of angular momentum, meaning that air farther from the center moves more slowly, while air close to the center spins with deadly velocity. A tornado's diameter may be hundreds of yards wide, but the most violent winds are often contained within a narrow ring called the vortex wall. This ring acts like a saw blade made of air, shredding everything it encounters. The tornado also behaves like a natural vacuum pump, pulling in warm air from the surface. As the air ascends through the vortex, it cools rapidly, condenses, and releases heat. This release of latent heat fuels the storm above, sustaining the updraft and strengthening the tornado from below. The engine becomes self-feeding. Warm air is ingested and cooled, condensation forms, heat is released, and the updraft intensifies, which in turn strengthens the inflow that keeps the tornado alive. The structure of a tornado. The interior of a tornado is a world few have ever seen and survived. While the classic image is a clean funnel shape, tornadoes vary dramatically in structure depending on atmospheric conditions and the terrain they pass over. Some are elegant tubes, narrow and sharply defined. Others are wedge-shaped giants wider than they are tall, appearing like moving walls of cloud. Still others split into multiple smaller vortices spiraling around a central core like dancers circling a stage. These subvortices are often the source of the most violent winds on Earth. Each one can contain winds far stronger than the tornado's general circulation, concentrating destruction in narrow paths while leaving areas only feet away relatively untouched. This is why some houses in a neighborhood may remain intact while others are obliterated. The interior of the tornado is governed by chaotic fluid dynamics, but there is organization within the chaos. The air spirals inward at the ground, rotates around the core, and then rises rapidly. This creates bands of alternating intense and mild winds, visible in some tornadoes as concentric rings. These rings are the signature of a powerful vortex, similar to the eye wall structure of a hurricane, but occurring on a much smaller scale. How tornadoes cause extreme damage. Tornadoes can produce some of the most violent forces in the natural world. Their destructive power is measured on the enhanced Fujita scale, which ranks tornadoes by the damage they cause rather than by direct wind measurements. This is because the inner core of a tornado is often too chaotic to measure accurately, and instruments placed in its path rarely survive. The damage from a tornado arises from several factors. Wind speed is the most obvious, but other forces are equally important. The pressure drop inside a tornado can cause buildings to explode outward if not properly ventilated. The inflow winds can push structures off their foundations even before the main vortex arrives. Subvortices create narrow swaths of destruction that resemble giant circular saw cuts across fields and neighborhoods. In the most violent tornadoes, objects become missiles. Wooden boards become spears capable of penetrating vehicles. Cows and cars can be lifted, carried, and dropped miles away. Massive steel beams can be twisted like wire. The tornado's rotation allows it to apply forces far beyond what straight-line winds could achieve. In extreme EF5 tornadoes, the combined effects of speed, pressure, and rotation make the environment equivalent to a moving blast furnace of air and debris. The life and death of a tornado. No matter how violent, every tornado has a lifespan. Some last only seconds. Others survive for over an hour. The life cycle of a tornado mirrors that of the storm that creates it. As long as the supercell's updraft remains strong and the inflow of warm, moist air continues, the tornado can persist. But once the balance of the storm shifts, the tornado begins to weaken. The first sign of weakening occurs when the updraft becomes displaced or disrupted. If rain-cooled air, known as the rear flank downdraft, wraps too tightly around the tornado, it can choke off the warm inflow that feeds the vortex. Without fresh, warm air rising into the storm, the tornado begins to narrow and weaken. The pressure difference fades, and the rotation slows. Eventually, the rotation dissipates entirely, and the vortex becomes indistinguishable from the surrounding storm.